right, so what I have on the itinerary for today is we have a lab to do for the last half of the class. For this first portion, what we talked about on Monday was that we could effectively analyze any steady state sinusoidal circuit in the frequency domain using DC circuit analysis techniques. So what I want to know from you guys is, what are the DC circuit analysis techniques that you don't remember particularly well or feel uncomfortable using? And let's review those in the context of a steady state sinusoidal circuit. Because we have all of the requisite knowledge, or at least we're supposed to at this point. So what are you uncomfortable with? And let's spend some time talking about that. Carter. You don't like source transformations. Does that mean that you would like to review how to do source transformations? Okay, all right. So do you want to work a problem involving a source transformation, or do you want to talk about the rules by which source transformations obey? Okay. Do you have any particular preference about practical voltage source to practical current source, or vice versa? Okay. So let's say that we following problem. Let's see, I'm just trying to make something up here. Would that help? Probably not. Let's see. So we're going to start in the frequency domain. So let's, for the sake of argument, call this 12 angle 0 degrees volts, and this current source 2 angle 10 degrees amps. Let's call this impedance up here ZA, which will be 10 angle negative 30 degrees ohms. This impedance here, ZB, will be 6 plus J2 ohms. Let's call this impedance ZC, which will be 9 minus J5 ohms. And finally, this impedance will be ZD, which we'll call 8 angle 15 degrees ohms. And let's say that we are trying to find this current IVS is a phasor quantity. Okay. So one way that we could potentially analyze this circuit, right? It looks like we'd probably try to do something wacky like a mesh, since there are 3 meshes here. Maybe some form of nodal could be a possibility as well, but since we're going to use source transformation, let's do that. So I would posit that we can do a single source transformation to turn this ugly looking circuit into a single loop circuit, for which we could apply just a single KVL equation in order to find our unknown quantity IVS, okay? So how would we go about doing that? Impedance ZB is connected in parallel with the series combination of impedance ZC and ZD. Is everybody okay with that? So we could replace several of these impedances with an impedance which I'm going to call ZEQ, which would be ZB times ZC plus ZD divided by ZB plus ZC plus ZD. That equivalent impedance, let's see, so we have 6 plus 2i times 9 minus 5i plus 8 angle 15. Excuse me. And then so I get an equivalent impedance of 4.722 with an angle of 10.843 degrees. I'm sorry, what? Okay. So all I'm doing here, just to be clear, is I'm saying that the impedance ZB is in parallel with the series combination of ZC and ZD. Okay. So I could redraw my circuit as follows: 12 angle 0 degrees volts. Here's ZA. Here's ZEQ. Here's my 2 angle 10 degrees amp source. And here's the quantity that I'm interested in. IVS, right? I can do a source transformation now where I will replace the practical current source on the right-hand side formed between the 2 angle 10 degrees amps current source and the ZEQ impedance with a practical voltage source that'll look something like this. Here's ZA. Here's ZEQ. Here's my voltage source that I'm going to need to determine the value of in a moment. Here is my quantity, IVS, that I'm trying to find. So the rules for source transformation obey simply Ohm's law, right? So the voltage drop across my voltage source on the right-hand side is simply going to be 2 angle 10 degrees amps multiplied by my equivalent impedance ZEQ. And so from this, I can see that IVS is simply, oh, what the heck happened there? 12 angle 0 degrees volts minus 2 angle 10 degrees amps times ZEQ, all divided by ZA plus ZEQ. And so give me just a moment to perform that indicated math. ZA 10 angle negative 30. I get 332.105, an angle of negative 29.446. Degrees milliamps. So let's talk about what we did in this problem just real quick. Not only did we do a source transformation, we absolutely did. We actually threw in some source combination as well, implicitly here, right? The reason why I say that is because the 12 angle 0 degrees volts minus 2 angle 10 degrees amps times the EQ represents the equivalent voltage for this final circuit. Like if we had lumped them together as a single voltage drop over those two impedances, ZA in series with ZEQ. All right, what else do we want to talk about? Bradley. Voltage division, okay. So let's say that I have the following circuit where I have 15 angle 90 degrees volts, an impedance ZA, which I'll have 8 minus J 5 ohms, an impedance ZB, which I'll call 2 plus J 9 ohms, an impedance ZC, which will be 5 angle 20 degrees ohms, and an impedance ZD, which I'll call 4 angle negative 10 degrees ohms. And I want to know this phasor voltage VD. All right. Again, a multitude of different ways that we can analyze this problem, but the suggestion here is to use voltage division. So what I'm going to do is actually apply 2 applications of voltage division to get that quantity, okay? So I'm going to call this voltage here VB. And I can see that VB is just 15 angle 90 degrees volts times. Bradley, let's talk about what we're going to do here, okay? So in my first application of voltage division, I'm trying to find this quantity VB, which represents the voltage drop over the 2 plus J9 ohm impedance in parallel with the series combination of 5 angle 20 degrees ohms and 4 angle negative 10 degrees ohms, okay? So in the numerator of my voltage division equation, I want the impedance that I'm trying to find the voltage drop over, which is the parallel combination of ZB in parallel with ZC plus ZD. So mathematically, that's going to look like ZB multiplied by ZC plus ZD over ZB plus ZD, excuse me, plus ZC plus ZD, like so. Actually, let me move this up because I've gotten slightly ahead of myself here. That's not what I wanted to do. I want to move it. Because this part right here actually just represents the numerator of my voltage division ratio, right? On the bottom, I want to have ZA plus that quantity that's in my numerator. So we have this big ugly monstrosity right here gives us the quantity VB. We can, in a separate step, we'll get to this in a second, see that VD is simply whatever we get for VB multiplied by ZD over ZC plus ZD. So 2 applications of voltage division will get us the quantity that we were looking for. So let's take just a moment here to do these calculations. Hoping my calculator doesn't run out of memory with me trying to type all of this in one go. We shall see. So for VB, I get 6.731 with an angle of 137.507 degrees. Volts. Now, for VD, I get 3.096 with an angle of 120.801 degrees. So as a refresher, the key to applying the principles of voltage division is that we want to make our impedances in this case look like several impedances that are in series. In this case, it's just two impedances. And we were able to, finding the equivalent resistance, or excuse me, the equivalent impedance of ZB, ZC, and ZD, we were able to apply voltage division to determine the voltage VB. And then once we know the voltage drop over VB, that is the same voltage drop that's applied over ZC in series with ZD. And so we can use voltage division a second time to get the voltage VD that we were trying to find. Anything else? We talked about voltage division. We've talked about source transformation. We've done voltage source combination today. I believe we did some current source combination on Monday. We did superposition on Monday. We did effectively Kirchhoff's current law with some algebra to set up a one equation, one unknown system on Monday. On some of your homeworks, you will be required to apply nodal analysis and mesh analysis. How many of you guys know how to enter complex numbers in MathCAD? Joel raised his hand, that's literally the only person. All right. So I'm going to pull up MathCAD real quick and just give you guys a very brief tutorial to try to help you out. Okay. Okay, so this is just going to be kind of a feature demonstration of MathCAD more so than solving a problem. Obviously, nodal analysis and mesh analysis in the frequency domain behaves exactly the same as nodal analysis and mesh analysis for DC circuits. Okay, there's nothing literally different at all, except that we now have to deal with complex numbers. Okay, so if I want to, what the heck is that? Give myself a voltage, let's just call it for the sake of argument, voltage A. To express it as a complex number in polar form, which is usually how I would do it, I would give the magnitude, which might be something like 12 volts, and then I need to give it a phase angle, okay? So to get the phase angle, we can click this operators button and then go down here to engineering and literally just click on this and it will give us the angle operator. But you may also notice that it says Control-Shift-P. So that's a keyboard shortcut to where we don't have to go up to this dumb menu over and over and over again. We can just press Control-Shift-P to insert that operator. So Control-Shift-P gives me my angle operator. Let's just say for the sake of argument that it's 78 degrees, okay? Now, by default, MathCAD expects the angles in radians. So if we don't tell the computer to use degrees, it's not going to. Now, if we click on this operator thing again and go down to engineering, here we go. There is a degree symbol that we can use. Notice there is not a keyboard shortcut. So we would have to constantly come into this menu and click this thing, which to me seems wildly annoying. So what you can do is literally just type in DEG, and that is effectively the same thing as the degree operator, okay? Outside the parentheses, then I would give this units of volts, okay? Obviously, I would enter a current in effectively the same way. So let's talk about an impedance. Let's say that I have some impedance ZB, and I want to put it in a rectangular format, right? So for rectangular format complex number, that's going to look something like 9 plus J3. If we put J3 in, it actually won't like that, okay? So instead, we can do 3j, and it interprets it correctly. So if we put j after the number, MathCAD interprets that as the imaginary operator, the square root of -1. If we put j before the number, it interprets it as an undefined variable j, and it's going to give us an error when we try to do something with it, okay? So 9 plus 3j is the correct way to do it. Very similar to calculators where you have to put it in as, 9 plus 3i or whatever. MathCAD is actually pretty smart in as much as it can use either I or j as the imaginary operator, okay? So let's say, just for the sake of argument here now, that we want to find, I guess I should have called this ZA, the current flowing through element A here. So IA, so we also have an issue here. I need to give this a unit because I prefer to use units. To get ohms, if we do capital W and then control G, sorry, I did hit shift G, not control, that converts that to a Greek letter. So lowercase w gives you omega, uppercase W gives you capital omega or the ohm symbol. So anyway, if we do IA is equal to VA over ZA and press the equal sign, it spits out a number. This number is in rectangular form, right? With I as the imaginary operator. Well, if we just mouse in this area and press the math formatting button down here on the bottom right, under the complex values menu, MathCAD gives us several options with which to display our complex numbers, okay? The first option is rectangular format with I as the imaginary operator. The second option is rectangular format with J as the imaginary operator. The third form is polar format with our angle expressed in pi radians. The fourth option is polar form with our angle expressed in radians. And finally, the fifth option is polar form with our angle expressed in degrees, which is the one that I prefer 99% of the time. So we can use MathCAD to literally give us the answer in the format that we want, just like our calculator and all that kind of good stuff as well. If you're setting up solve blocks and all that kind of stuff using complex numbers, set it up exactly the same way that you would for a DC quantity, except initialize all your variables as complex numbers. So instead of saying, I guess that this variable has a value of 1, now say, I guess that it is a value of 1 angle 0 degrees or something like that. Any other questions on setting up MathCAD things? Other than these little nuances, it's literally the exact same thing as the DC analysis that you guys have done. All right, so just to reiterate, it is super, super important to remember to put this DEG thing here, okay? I guess actually, let me show you another quick couple of things, okay? So if I do the absolute value of VA, that gives me the magnitude. If I do the argument of VA, that gives me the angle in radians, where I can just type DEG to force it to give it to me in degrees. If I do VA and then make sure it's highlighted, I do Control-Shift-9, that puts a bar over the top. That bar over the top is not how we designate a complex number. In MathCAD, that bar over the top denotes the conjugate operation. So we can force it to do the conjugate for us, which we can verify that this is correct. 12 angle -78 degrees. All right, so conjugate is Control-Shift-9 or Control-Shift open parentheses. So, can't think of any other operations that you guys might need to know off the top of my head right now. When we get into complex power relationships, we'll probably revisit MathCAD again. All right. So any DC circuit analysis techniques you guys want to see utilized in the frequency domain? I typically don't put dependent source problems on exams or anything like that once we get into this steady state sinusoidal analysis, just because I feel like it's mean enough to make you keep up with all the complex math. Okay, I'm not saying that you won't see something like that in your homeworks or anything. Literally the exact same rules would apply as what you did in a DC circuit. So it's nothing different there. But on your exams, I wouldn't expect to see any, or at least on the steady state sinusoidal portion of your exam, I would not expect to see any dependent sources.